Good morning, everyone. It's my pleasure to introduce our work to you, and we apologize for our absence because of visa problems. I'm Zheng Zheng, an associate professor in Beihang University of China. This work is collaborated with Professor Zheng Yu Zhang and his group members from Institute of Software Chinese Academy of Science. The following includes our email addresses. I wish you can give us as more as comments with mails to improve this work. This is the main contents of this research. It mainly includes 5 parts. After a simple introduction of statistical software fault localization, we explain our motivation and technique in detail. Finally, preliminary experiment result and the conclusion will be given. First, let's look at the framework of statistical fault localization techniques. They compare spectra abstracted from both field runs and non-field runs to evaluate the suspiciousness of each element in subject program. According to the focused elements, we separate these techniques into statement-based methods such as triangular and predicate-based methods such as CBI, and our work belongs to predicate-based methods. Although statistical fault localization techniques are reported successful, their effectiveness to locate faults is unavoidably influenced by the characteristics of input data. One of the factors negatively affecting these techniques is the phenomenon called coincidental correctness. It means no failure is detected though the fault has been executed. The execution profiles of non-field runs that coincidentally manifest no abnormal behavior may closer to those of field runs, because both of them trigger the fault. This may have a negative impact on the accuracy of statistical fault localization techniques. Previous studies show that this phenomenon is prevalent, and they try to find out the coincidental correct runs and remove them from input. However, this job is difficult because we don't know which statement or function is faulty at the beginning, and this work may lose some useful information. So, a question arises: can we allow the existence of coincidental correctness and locate a fault with presence of it? In the following, I will show the motivation of this work using a piece of code. This is a program used to calculate the maximum value among 3 integers. A fault is stated in the statement line 5, and the comment is the correct form. To locate the fault, the 6 cases are used. We notice that although T3, T4, T5, and T6 have executed the faulty statement, only T5 and T6 generate unexpected output. Following previous work, we install 7 predicates in the program, and they are noted as P1 to P7. We also use the form X to Y to record the dynamic spectrum in a program run. For example, the 0 to 1 of predicate P1 and the test case T2 means P1 is evaluated false once and never evaluated true. In the program, we label 3 categories of predicates: neutral predicates, fault-leading predicates, and fault-led predicates. Each predicate may have more than 1 labels. For neutral predicates, its existence does not correlate with the existing status of the fault. And the fault-leading predicates leads to trigger or skip the fault. The triggering fault determines to exercise or skip the fault-led predicates. With such a criterion, the 7 predicates are separated into three groups, in which P1 is a neutral predicate, P2, P3, and P4 are fault-leading predicates, and the rest of them are fault-led predicates. Okay, let's explain them in further. For a neutral predicate, its dynamic spectra in every runs resemble each other. In our motivated example, the spectra of predicate P1 in all runs are the same. This can be understood that the neutral predicates often have less relationship with the fault, so that their behavior make less difference in every runs, no matter it is field runs or non-field runs. For fault-leading predicate, its dynamic spectra in coincidental runs are similar to those in field runs. For example, let's look at the predicate P2. Its spectra in coincidental runs T3 and T4 are identical to those in field runs T5 and T6, while it is different from those in T1 and T2. This can be explained. The execution paths leading to a fault often concentrate into small clusters, and both the coincidental and field runs trigger the fault. So the overlapping of spectra in field runs with that in non-field runs is 100% in this example. For fault-led predicates, we can see that its dynamic spectra in coincidental runs are similar to those in successful runs. The spectra of predicate P5 in coincidental runs are identical to those in successful runs T1 and T2, while it is different from those in field runs T5 and T6. This means that the abnormal status in coincidental runs may somehow have been repaired and is not propagated into the output. So the behavior of fault-led predicates in coincidental runs are similar to those in successful runs. And the overlapping of spectra in field runs with that in non-field runs is zero. Such observation inspires us to utilize the spectrum distribution in different program runs to distinguish the fault-leading predicates from the others. And from above discussion, we find that we can rule out the fault-led predicates by comparing the extent of overlapping. However, there are still some problems need to be solved. A predicate can be evaluated more than once because of the presence of loops. The offsite overlapping can also be a good indicator. The neutral predicates have high overlapping and are mixed up with the fault-leading predicates. Thus, let's explore the problem further. In the following, we will introduce our technique inspired by the observations. In brief, our technique consists of 4 steps. The same as traditional techniques, we collect the dynamic spectra and calculate the suspiciousness of each predicate to generate a rank list. The difference is that we calculate the suspiciousness of each predicate in 2 steps. First, we calculate the overlapping of spectral distribution to rule out the fault-led predicates. Next, we use the inter- and intra-class distance to pick the fault-leading predicates out of neutral predicates. In the process, step 2 and step 3 are the keys, and we will discuss them in depth in the following. In our proposed technique, we introduce the Batakaya coefficient to measure the overlapping of spectra of field and non-field runs. Batakaya coefficient was introduced to the field of machine learning and pattern recognition to measure the amount of overlap between two statistical samples or populations. And the coefficient can be used to determine the relative closeness of two samples being considered. It is used to measure the separability of classes in the classification. The measurement is proved to be the upper bound of Bayes' error, which directly related to the overlapping of two models. Based on the Batakaya coefficient, a measure of distance called Batakaya distance can be developed. Let's look at the equivalence. Here BC is the Batakaya coefficient, and P is the conditional probability. And next, we use the Batakaya distance to rank the predicate by referencing their overlapping value in the descending order. After using this distance, the top-ranked predicates may include fault-leading predicates mixing up with the neutral predicates. In order to pick out the fault-leading predicates, we introduce the intercast and the intracast distance. The intercast distance is the Euclid distance between the mean value of evaluation bias for Pj in field and non-field runs. As the spectra of a neutral predicate are similar to each other in every runs, the intercast distance can be used to rule out the neutral predicates. The larger intercast distance is, the more suspicious the predicate will be. However, the fault-leading predicate cannot be located only by using the intercast distance. Also, we developed the intracast distance to evaluate the density of samples, and the intracast distance is evaluated as this formula. If two models are different, usually we expect the intercast distance is long, while the intracast distance is short. So we normalize the intercast distance as this form. And this step may decrease the rank of neutral predicates without affecting the relative orders of fault-leading predicates and fault-led predicates. After step 2 and step 3, a ranked list of suspicious predicates is generated, and developers can follow this list to locate the fault. In the following, I will show some empirical evaluation to demonstrate the effectiveness of our technique. In our experiment, Siemens Suite, Space, and 2 Unix program flags graph are used to evaluate our technique. There are totally 171 different faulty programs. This table lists the main information of the subject programs. We compare our technique with the CBI Sober, Wilson, and Mann-Whitney, and the effectiveness of the metric called p-score. The p-score means the percentage of predicates that need to be examined in order to locate the fault. This figure illustrates that our technique can outperform representative existing techniques. This figure depicts the overall effectiveness of each technique. The x-axis shows the predicate examination efforts, which means p-score. The y-axis shows the percentage of faults located with the given predicate examination efforts. The curve of JB, which stands for our technique, is shown in bold, and the curve of other techniques are shown with different colors and markers. It can be seen that for the 17140 versions in all the programs, our technique always locates more faults than the other techniques when using predicate examination effort of 10% to 90% as a checkpoint. From the experiments, we can see our technique has an overall advantage to the other techniques in locating faults in the subject programs. At last, we conclude our work. In this paper, we propose an idea to use the presence of coincidental correctness to locate faults. First, we analyze the predicate in sequentially executed program and label them into three categories, namely neutral predicates, fault-leading predicates, and fault-led predicates. We mirror the overlapping of the spectrum distribution to rule out the fault-led predicates. Then we surprise the neutral predicates by assessing the interclass distance of spectrum in field runs and non-field runs. An empirical evaluation shows that our technique is promising. Because of the space limited of this paper, we don't show that all the experiment results. Thank you.